Well, the sine law works because of this height. It's to do with this height of this triangle and relating everything to this height. So basically what we can say is that if we want to calculate the height of this triangle here, we can take the hypotenuse and multiply by the angle. Okay, so we take A sine B gives us the length of that height. Or if we write it in the sine form, we can say that h over side A is equal to sine of beta. Okay, we know that, yeah, height over A is sine of this angle here. And we could do the same thing for the other angle here too. We can just say that, B, the length, the hypotenuse here, B times sine A equals the height of this triangle. Or in other words, we can say that the height divided by length B is equal to sine of alpha. Okay, so this expression then becomes this one here. This expression becomes this one here. And we can make them equivalent to each other. Okay, so if these are equivalent to each other, then we can rearrange this and say that, well, we can put the A with the sine alpha side, and we could put the B with the sine beta side, and then we end up with them both equaling the height of this vertical line. Okay, the height of the triangle, and we can then say that they are equal to each other. Okay, so these are equivalent to each other. And we could say then set up this same argument for the third side, and we can say that the sine of the angle and the opposite side ratio is equivalent to the angle and the opposite side ratio of the same triangle. And then we can set up the third ratio, the sine of, C, angle C, to the length of side C is equivalent to for all three sides of any triangle. So this is why the sine law works. Basically, we start with this calculation for the height, and we can see that we can calculate the height from this perspective, from the left-hand triangle. We could do the same thing from the right-hand triangle, and then just doing a little bit of algebraic rearrangement, we can come up with our sine law ratio. Okay, so this is why it works. And in fact, this is a proof of why it works. So we alluded to this before, but there is this issue of ambiguous case. Okay, so when we have angle side, so we have here, let's say that we know angle B, we know the length of side C. So maybe I'll just highlight the angle side. So the angle side is going to be this angle, this side, and this side here. We could have this angle, this length, and it could form this black triangle here. Okay, that's perfectly legitimate, and we form that one triangle. However, since the length of side A is not fixed, okay, because that's not known information, it's possible that this side B can be oriented so that it touches the side A at this point down here, okay, which I'll highlight. This green dot right here, it could just form at that point. And by doing so, we have two different triangle possibilities given this information of angle side. Now this does not occur when we have two angles and a side. Okay, so when we have two angles and a side and we use the sine law, we don't have to worry about this. However, when we have angle side, two sides and an angle, this issue can happen. Okay, because we don't have the two angles. Given two angles, we fix the shape of the triangle. Given just the two sides and an angle, we don't fix the shape of the triangle, which means that there are two possibilities. So this is a problem. So what do? And how do we resolve this? Okay, well, if we take a look at this picture here, when we solve this, what we're going to do is end up solving for angle B. Okay, so we have angle C. So we have B and angle B, opposite angle side pairing, and what we would end up doing is solving this opposite angle side pairing here. And so the issue is there are two possible angles that can be solved for here if B is oriented like this, or this angle here. Okay, this angle and this angle, they are different angles. One is obtuse, one is acute, and they're both formed by this length of B. So how are they related? Well, they're related in this way here. That angle there and that angle there are the same. And so what ends up happening is, if I want to solve for this red angle, I can take the original green angle that I would solve for here and find the complementary angle, the supplementary angle here, the red angle, by just subtracting from 180 degrees. So that's quite easy to do. Now, it is also related, and this is the connection that makes it a lot easier to do as well. It's also related to theta 1 and theta 2 when we do arc sine. Okay, so in the unit circle. Here is theta 1, and theta 2 is going to always be 180 degrees minus theta 1. Okay, because remember there's going to be my theta 1, and because the symmetry of sine, it's just going to go backwards like that. So theta 1 and theta 2 here, this is what we dealt with in the circle. Anytime we solve for sine, okay, or undid the sine, we always had these two angles that we had to worry about. Well, this is the same thing here. In fact, they're exactly the same angles. We have theta 1. Our calculator will give us the acute angle, and we can find the obtuse angle by subtracting from 180. It's the exact same formula. Okay, slightly different diagram, but the exact same formula that gives us this other angle here. So I'm going to call this one theta 1, and the other angle here is theta 2. And this is the same theta 1 and theta 2 we talked about in the circle. Exactly the same, and it comes about for the same reasons. So when we have angles side side, we have to worry about this theta 2. Okay, and this theta 2 issue is the same formula as we found when we were undoing the sine ratio when we had to find theta 1 and theta 2.